My name is Sochivoath. You can call me Sochi, and my partner is Kien. And today we're going to present our project on car detection and speed estimation. As Ajahn Kwan has said, we are second-year students, and this project, at the beginning, we never done anything like this, and to do this was very interesting, and we learned a lot. Now, moving on, I'll start with the presentation. Not working. Kien? Okay. So first off is the content. The content will be divided into four parts: the objectives, the motives, our previous attempts, and the materials of our current model. So first, the objectives. The objective is, there are three main objectives: to detect vehicles accurately, to track them properly, and then to provide a velocity estimation. Now, we say estimation because due to the current situation, we are unable to go out and we are unable to take measurements or unable to actually look at cars and take live videos. So what we've done is we've done what we can sitting behind a screen and make a proper velocity estimation using the materials we've had and using whatever we can take online. Now, the motives for this project: why analyze vehicles? So we analyze vehicles because this is very flexible and can be applied to many different areas. We can use it for vehicle counting, classification, license plate recognition if you want to catch speeding criminals. We can track vehicles. It's useful for security in parking lots. We can use this. We can use the data that we get to find out rush hours. We can use it to find out which cars are like who likes red cars more than blue cars if you want to win a bet or something like that. So we use speed estimation. However, this thing can really branch out into a myriad of different different applications. Now, first off, tackling the problem. To tackle the problem, there are three main parts. The first part is, of course, detecting the car. We want to be able to accurately detect the car because it's a vehicle speed estimation. We do not want to detect birds. We do not want to detect random walkers or joggers on the street. So first, we want to detect cars accurately. After we are able to detect the cars, then we can, right? Yeah. Okay, so continuing on, after detection, then we can associate and we can track the cars. So the tracking is very important because we want to know the motion of the car and how it moves. And this is important for speed because faster cars move faster. And we want to associate the cars because in many cases, there are multiple vehicles in the same frame or in the same video. So because of this, we want to make sure that we are getting the velocity of the same car as the frames move on. And after that, we can estimate the speed and get it properly. Now, our previous model. For previously, when we started out, we decided to use MobileNet SSD and Caffeine model for the detection and a Centroid tracker for the association and tracking. And together, it'll give, together we can get the velocity like this and it will display like this. However, after multiple tests and after multiple runs and after multiple modifications, we decided that this was not a good model at all. And the issues are defined as follows. Number one, it only works from the side view only. This is not practical whatsoever because in the real world, we would want the camera at an elevated angle to look down onto cars. And for this one, working well only from the side view just is not practical at all. It is also, this model also better detecting one vehicle at a time. And as I've said before, realistically speaking, there will be multiple vehicles on the road at the same time. And so if we detect one vehicle at a time, there's no need for this model. And the next one is that it has very bad estimations at higher speed. This is because of the MobileNet SSD, which stands for MobileNet Single Shot Detection. The MobileNet Single Shot Detection was made for low computation computers. So what this meant is that it could run well on things that didn't have GPUs and things that didn't have a strong CPU. However, this meant that the detection throughput would be much lower and the accuracy would be much lower. And since we were only able to estimate because we were unable to go out, we decided that we would sacrifice computation power in order for the accuracy. And because of this, we use the current model. Currently for detection, we use YOLO V3. This comes with classification as well. As you can see, it says truck. This is a very nice feature as well, but for this one, it is redundant. We just need it to detect vehicles. And then we use Kalman filter. The Kalman filter will go into details later, but For now, the Kalman filter is just used to track and associate the vehicles. And then together we get the velocity to provide a final result of this, where we can see the detection, we can see the prediction, and then we can see the velocity as well. Now, detecting the cars, this is the reason why we use MobileNet, why we use YOLO v3 instead of MobileNet SSD. As you can see on the graph, the MobileNet SSD has a low throughput compared to YOLO. What this means is that it detects at a slower rate than YOLO, and this isn't good, especially in the cases where the cameras aren't really good. The cameras have low FPS, and this just makes MobileNet very unreliable and unable to accurately track cars. And so we decided to use YOLO for this. Now, the reason why we use YOLO is because it's also similar to MobileNet SSD in the sense where it takes one shot. You only look once, hence the name. So it puts a grid onto an image, and then it uses bounding boxes and confidence and the class probability map to make final detections. We use YOLO v3 instead of YOLO because the original YOLO and tiny YOLO are very similar to MobileNet SSD in terms of performance. And so there would be no point. We use YOLO v3 because, as I said before, we would rather much sacrifice the computation power for the accuracy. Because with an accurate detection and accurate tracking, then we are more able to make a better estimation of the thing. Now, then the other improvement that we did was the ROI. So originally, when we first started out, we would detect throughout the entire frame. And this was very inefficient, to put it bluntly, because what this meant was that we would have to go from the top left corner and scan to the bottom right corner, and this just wastes time. And we could not afford to use any more computation power because of the YOLO that we decided to use. So instead, we use matplotlib, and what matplotlib would help us do is to manually select which parts of the road that we want to do, or which parts of a frame that we want to detect in. And this makes it very flexible, so we can apply our program to many different roads, into many different environments, as well as it saves a lot of the computation power. And this computation power just means that we can use it to improve the performance and the accuracy. And from here, we can see the before ROI and the after ROI. So the before we set the region of interest, which is what ROI stands for, it would detect the right side, which we are completely uninterested in, and it would detect the far end at the back where we cannot even see. So there would be no point of this. Now, after ROI, we can see that it will only detect what we're interested in, and this just makes it much more efficient and much more a much better model than how we do. Now, moving on, my partner Kien will take over.
Okay, so thank you, Sochi. Now I'm gonna introduce to the tracking part of vehicles. So for tracking, we decided to use the YOLO v3 along with Kalman filter. But before choosing these, we have another option. Our first option were cover model and center trackers. The reason why we choose YOLO v3 and Kalman filter instead of keeping the center tracker is that even though the center tracker got a tracker word in the name, it actually only do the association, while Kalman filter actually do both association and tracking. So for this reason, I believe that YOLO v3 and Kalman filter is a better choice. As you heard, the first group in this presentation, like Kalman filter, like is a linear quadratic estimation based on the estimation that you have observed, based on the measurement that you have. And I'll explain how we apply Kalman filter in this project. First of all, on the screen, I have a car. YOLO v3 will provide a correct prediction, which is the green box. Now, next step, Kalman filter will provide the red box, which is the predictions. This is the future move of the car. So if the next move the car is correctly in the red box, the red box becomes the green box and is another correct detection. The process will continue. So that's the first scenario. But in the second scenario, when we have another car and another detection box, but in this case, Kalman filter predict the wrong position of the car, which means the car is not in the red box anymore. So in this scenario, the car will be considered as another car and another green box will be provided and the process will continue. But whether in both scenarios, we will have the, like whether the prediction is correct or wrong, we still have the direction of the car, which we know how the car is moving. Why how the car is moving is so important and why Kalman filter is so efficient in this case? I'll show you. I have a picture on the screen. with the road. So we can clearly see that how the car is moving and what will be the direction of the car, which is the red arrows I have on the screen. So if there's a car on the screen, which is the green box over here, it can only move in this direction. So for this reason, Kalman filter can easily predict and guess the future move of the car. So for the next part, the velocity estimation. For the velocity estimation, we decide to use OpenCV and Kalman filter, and we base on two main formulas. The first formula will be d pixels, which calculate the distance between two coordinates in pixels. The second formula is velocity, where there are three parts. The first part is d pixels divided by ppm, which is pixel per meters. This part is to convert the distance from pixels into meters. The second part is that we times it with FPS, frame per second, to calculate the velocity in meter per second. And the last part, we times this with 3.6, which convert the meter per second to kilometer per hour. I'll explain further how this formula is applied. Okay, so again, we'll have a car and a correct detection. So after we detect the car, we will have the x0 and y0, which is the coordinates of the first movement of the first position of the car. So after we predict and we have the next position the car will have x1 and y1. So with these two coordinates, we can easily calculate the distance between these two by using the d pixel formula. Then we move to the velocity part when we take the d pixel that we calculated, divide by ppm, which we decide to be 8.8, times with fps to be 45, and times with 3.6. I'll explain further why we choose ppm to be 8.8 and fps to be equal to 45 later. But because the speed is not constant, so every time the car moves, the speed will change. For this reason, we decide to calculate the speed 20 times in 20 different frames to get the average results. So I believe that this will increase the accuracy of the speed estimation. So as I mentioned before, the velocity estimation has tackled one biggest problem is that because of the COVID-19, we are not able to get outside and set up our own camera and take our own samples. So we are lack of the real samples to estimate the speed. And also because we don't take our own camera, we also don't have enough information about the camera position, like how high we put the camera, what is the angle of the camera compared to the car, compared to the road. So if we don't know anything about the camera position, then the data from the camera is not reliable. However, we have come up with a solution that can handle this problem, that instead of using only the camera information, we also estimate the distance by using the real car size. So we have some sample cars over here with the length of the car. So we also based on these to actually estimate how many pixels compared to how many meters. This is our final project demo, as you can see. There's the pink and the light blue blocks. That's the YOLO V3 to detect the car. There's a dark blue box that is provided by Kalman filter. That's a Kalman filter prediction. There's the red number, which is the ID of the car. That's we use to track the car. And the green number is the velocity of the car. So after running the program, we have recorded the first 50 cars. The average speed that we have recorded is 63.5 kilometer per hour, and there are 5 fails detection, which is 0 kilometer per hour. Why there are fails detection? Because for sometimes the car is moving too near to the camera, which is too big, and this may cause some fail detection by YOLO. And also, because I have mentioned before, I calculate the speed by 20 times in 20 different frames. So if the car is not showing up for enough 20 frames, then we're not going to take that as a reliable speed estimation, and we don't take that as a number.
Okay, so for the final words, we'd like to say that for this project, we had a lot of limitations, as my partner Kien has said, there was a lack of information, as in the camera angle, the actual distance of the road, how much the frame per second of the camera is. We had to do a lot based on things that we had, based on the internet, we had to think a lot outside the box using real world, using the car measurements instead of using other things, finding out different methods and applying it together. However, we came up with this model, and with the concept that it can be applied to many different things. It could be very flexible, and it can achieve a lot of goals at the same time. And because of that, thank you for listening to our presentation.